Okay, we're back with Wavy Physics episode 10. It's been a minute since I've uploaded a video. There's been a lot going on. I've been working on a lot of things. I broke my knee and not least this whole virus epidemic. But what I wanted to record today was a little video on CFD. I had a couple of requests from some of the followers and some friends to put together a little video introducing CFD. I guess it might be one of those things where past uni or at work, you're not really going to be too familiar with it. I use ANSYS FLUENT to do my work. So this video is just going to be a short clip. I'm going to take you from the finished CAD to a complete simulation and just go through the simulation setup, running the sim and doing some very simple post-processing. The part I'm going to use is a wing that I designed, so we're going to keep with the motorsport application, and by the end of the video you should be comfortable with taking your finished CAD design to run in a simulation. Okay, so starting with CAD. This is going to be the same for all CAD packages. I'm using SolidWorks, but it's going to be the same principle throughout. So the first thing you need to do is take your 3D model, whether that's a wing like I've got here, or some kind of other flow device, or even a full vehicle. You need to take the 3D model and put it into a different format, which your CFD package will understand. So I'm using Fluent, and I know that step file is what it works with comfortably. So let me save it as a step file. Alright, now we want to open Fluent, and you look in your toolbox here. You've got a choice of workflows to choose from, and I'm doing a fluid simulation, so that's what I need to choose. And it gives you a workflow. So you start with a geometry, which is like your imported CAD geometry. You set up the model that way. Then you got to mesh it. Then you got to actually set up the model. And after the setup is complete, the setup being setting your air velocities, your fluid types, any other experimental conditions, you simulate. When the solution is complete, you go into the results, which is post-processing. So let's start with geometry. Okay, so once you've opened Design Modeler, the first thing you need to do is import your external geometry file. So click that, find your part, and import it. So the main purpose of this stage of the simulation is to show the CFD simulation what geometry you're using, and then ultimately to define the computational domain. So what the computational domain is the volume that the CFD program will simulate the airflow over. So there are some considerations for the computational domain. The first one is that you don't want to make it too big, as that's going to be very computationally expensive. It's going to take a long time to simulate and require a lot of power. But you also don't want to make it small enough that both you and the CFD software can't understand the flow conditions around the part. And that does actually also influence the results. So you need to allow the program enough time to simulate to a degree of accuracy that you're happy with the size of the computational domain. So let's do that first. In Fluent, that's done usually with something called an enclosure. So if we click the enclosure, we get to define the size of the enclosure by the positive and negative values of each axis. So if I just leave it as that and click generate, you'll see that it makes quite a small box around the part. So we actually want that bigger. So for this purposes, I'm just going to make that 300. Of course, this isn't really a real study. I'm just trying to talk you through the process. This is going to be determined by your actual project. So that's something a bit more realistic. So through a bit of experience and foresight, it's useful to set names to each of the extents of the enclosure and to the airflow. And what they serve to do is allow you to quickly set boundary conditions for each of the faces. In post-processing, to quickly take data and have a quick reference. So for example, naming the rear face of this enclosure will allow me to establish the mass flow out of it. Naming the aerofoil will allow me to understand the forces acting on it, so lift and drag. So I'm going to do that at this stage to make my life easier later. Okay, and now it gets a little bit counterintuitive, but you need to subtract the actual imported CAD away from the enclosure, away from the flow domain. And what that does is create a solid surface to represent the geometry of the part. So you do that with a Boolean operation, and that needs to be a subtract. Then you need to subtract the target body, which is the flow domain. And then the tool body is then the wing. So a bit counterintuitive, but that's just the way Fluent works. Then when we've done all that, an important consideration is that in a similar way as I was saying, having a domain too large is computationally intensive, you can assume that a solution that will get you a good approximation is to treat the airfall in a symmetrical manner. So you can assume everything around the center line, everything to the left and right would be a mirror of each other. So you can actually do that at this point by cutting the domain in half with a special tool called symmetry. So I'll do that. I need to correct an error I made in that when I subtracted the geometry from the domain, it then got rid of my name selections. So bear with me while I correct that. You're also going to want to create a name selection for the symmetry face that we now have after the symmetry operation. So with that done, we can then move into the meshing. So once you open the meshing module, you're presented with your geometry. And I'm not going to talk about how to correctly mesh a part in this video because that's quite a complex subject and it's going to be a long explanation. But what I'll do is just show you how to create a general mesh and how you can refine that slightly. But the first thing to do is click Generate Mesh. Okay, so once the operation is complete, you're presented with your mesh. And if you've got any experience with meshing at all, you'll see that this is really coarse and it's not really going to provide you any representative data. Let me just show you a bit more of the mesh so you can understand it a little bit better. You can see our model part in there, and it gets a little bit better around the leading edge of the airfoil, but it still can do with a lot of refining. So let's do that. So if this was a proper study, I'd want to spend a bit more time on it, but for demonstration purposes, I think this is not too bad. So with that done, close that off, and we move into the setup phase of the experiment. So I'm using two processes as this machine has two cores. Alright, so to configure the simulation or the experiment, it's pretty much just a case of working through this tree and putting in parameters as you need. So starting with the general tab, we need to stay with the pressure-based solver because we're using incompressible flow, so that's fine there. The velocity formulation can stay as absolute. And the time, this is quite an important one. So a steady state based simulation just kind of takes a snapshot of the flow at any point in time. It doesn't take into account transient flow phenomenon or time-based things like vortex shedding. So you can lose quite a lot of detail, and you also can't produce an animation, which you might want to do at some point. The steady state simulation is a lot easier computationally, and the transient simulations can take quite a lot of time to get you to a decent accuracy. But for today, we'll start at steady. And so the models we use, we don't need multi-phase because we've only got one phase of matter. We don't need energy, we're not taking into account any heat. It's also very crucial to your results that you select the right turbulence model. There's a lot you can choose, and each of them have their specific areas that they're most focused to. For example, some are better suited to rotational flows, some resolve the boundary layer a bit more effectively, But a good all-rounder for most calculations is the K epsilon model, which generally does a good job of modelling turbulent kinetic energy, K, and the dissipation of turbulent kinetic energy, which is epsilon. So radiation off, heat exchanger off, species, no, there's no combustion or anything like that. And the rest of it stays as off. So it's quite a simple case we're running today, only one model. The materials. So the fluid we need to use is air, or we have air configured here. Aluminium, the solid, doesn't really matter. We're not worried about heat or any mechanical properties. Cell zone conditions. Okay, so the solid is the computational domain, which we discussed in the design modeler. It could be a different name, but it stayed as solid. And we need to just make sure that the fluid used here is air, which we've already configured in the materials section. And as you see, make sure that's fluid. Boundary conditions, that's an important one. So I want this simulation to just be an arbitrary air volume, say, in free space that we just take a snapshot of and run a simulation. So that means the boundary conditions on all the exterior faces you see here must be a pressure outlet. So the airfoil is the name selection we chose earlier. That's a wall that's impervious and basically denotes the geometry. The inlet has the velocity inlet boundary condition, and we want just use an arbitrary air velocity of 40 meters per second, and that's normal to the boundary. The interior of the solid, so that's the interior type boundary condition. We can leave that there. Fluent picks up the designations you give to the named selections and picks boundary layers automatically. So you can see the outlet has already been described as a pressure outlet, so that's accurate. So we just need to make sure the rest of them follow suit. And you see here why it makes life easier to actually label your surfaces. Okay, symmetry, again, picked that up, so that's fine. So we should have 5 pressure outlets and 1 inlet. So velocity inlet, 1, 2, 3, 4. And symmetry, okay, which is 5. So 4 pressure outlets, 1 inlet. Okay, so that's that part. The solution methods, none of this is really so important today. As you become more familiar with CFD, you use these things to help with your convergence and how much accuracy you need from certain equations. But then that leads us on to initialization. So you need to initialize the solution, and what that does is basically provides a set of initial values for each cell. So the way I see that is it just gives the equations some initial values to start calculating from. Hybrid initialization is fine, and it will complete, as you'll see, 10 iterations, which is configurable, but 10 is okay for a default. And what you should see there is the scalar quantity here falling, which is indicating convergence. And once it converges to a certain point, you can be sure that the simulation will finish. If it doesn't converge, and the simulation will usually tell you, then it might mean that you need to look back at your mesh. Perhaps you've got some kind of irregular mesh or some kind of weird geometry effects going on. But for this time, it's fine. And then we run the simulation. So the number of iterations, that's important and varies case by case, but basically you want to give enough iterations that the simulation converges or reaches an acceptable level of convergence. And that's going to change for each situation. Let's just put in an arbitrary value of 250. I'm sure that's going to get us, again, something that's reasonable enough for today. So now we calculate that. Alright, so the simulation's complete. You can tell by the residuals plotted in the upper right box that they're fairly constant, which is good. K and epsilon have been having a little variation here. You can see there's a kind of up-down cycle. That might mean that the simulation needs a transient-based solution to give you any accuracy, but it's likely that we have convergence here. If the residuals were a bit more erratic, you might have to question what's going on and look at your setup a bit closer. So based on these quick results, I'm gonna now move into the post-processing. Okay, so we're in the CFD Post. This is the post-processing suite of ANSYS FLUENT. And what you can do here is basically visualize and take data from your results. So you can see here we've got the airfoil geometry and you have the computational domain. And you have basically vectors, contours, streamlines, particle tracks, and volume rendering to play with. You can create locations from which to plot your results. So I'm just going to start by making a plane. And I want that to be in the XY, I want that to be an XY plane. And I want it to be offset from by 300 millimeters in Z. So there's our plane. And what I can do with that now is plot pressure contours. So if I put the location as plane 1, pressure, I've got global pressure contours. We can see the pressure over the airfoil. Let me just hide that and make it a bit easier. Okay, so you can see, I'm sure you're familiar with scales, contour scales. So it goes from blue to red in terms of pressure. In this one, we can change that to velocity. So you can see we've got a high velocity on the underside, which means that you've got a lower pressure. We can add a bit more detail here. We can add 200 contours instead of 11, get a bit more resolution. Oh, sorry, let me hide that plane. And yeah, you can see there's some weird effects going on at the bottom here, the bottom of the domain. Likely due to the fact that it wasn't big enough. So there's some strange, I don't know, maybe there's some reverse flow or something going on there. So we can do streamlines too. Let me make a streamline. So with this 3D streamline, let's start from the inlet. Let me turn that pressure contour off. And what that's going to do is basically release particles of air, and you can track where they go. So you can see in this area there's a vortex, or the beginnings of a vortex, which is what you might expect. Then you can also do a surface streamline using, for example, the plane that we've got here. So you can see in the single plane how the airflow is moving. Vectors is quite a useful one, so that allows you to see any span-wise flow or other interesting effects. Same again there. So each particle then has an arrow which shows you where it's going. Yeah, you get the picture. Whatever you might think will help you visualize and understand your flow a bit better. There's also a cool feature, if you click on calculators and then function calculator, this is very useful for aerofoils. So you notice earlier, or you'll remember earlier, I named the aerofoil for reference a little bit later on. So with this, we can tell the lift and drag forces. So we can calculate the force in X on the aerofoil, so that's 22 newtons, and the force in Y, which is now lift. So there we've got our lift and drag numbers. This aerofoil is producing 195 newtons of lift in negative Y, which is downforce, so you'll understand this minus here, and this is drag in positive X. So that's pretty much a guide to CFD, what kind of things you can do with it and how you use it. Obviously some of the things I've discussed today are specific to ANSYS FLUENT, but there's going to be other things that are global for other simulation software. There's always going to be post-processing, there's always going to be choosing a turbulence model, etc, etc. I nearly forgot. So, due to the symmetry condition we put on the domain earlier, we've only been looking at half of what would be a realistic flow domain. So what you can do is create a mirror image around the symmetry plane. Just click the wireframe at the intersection of the model with the symmetry plane and select reflect or mirror. And let me just show you that with a pressure contour on the aerofoil. And I think that is a good place to end. In most cases in motorsport, there's obviously a clear methodology between running your CFD and verifying your CFD results with wind tunnel or track-based testing. And I did actually just cover that in an article I wrote for Race Car Engineering magazine on scale wind tunnel model testing. So if you're interested in reading a bit further, check that one out. But yeah, there's your intro. It should at least allow you to get yourself started and develop your knowledge a bit more, play around with the software. There's a lot of resource online, like in forums and YouTube. So if you are stuck, there's plenty of stuff out there that usually get you out of a jam. So I hope you enjoyed that, and I hope to be back a bit more frequently in the future. But yeah, running a consultancy and trying to go in this direction and that direction requires a lot of focus. So videos is obviously important, but sometimes I have to just be realistic with my workload. But I'll be back as soon as I can.